Good morning. This is Mr. Herman. This video is going to be about interpreting tables of exponential functions. So we're going to start off with growth and decay. So we've been talking about exponent properties for a while now, and we're going to start to look at tables to try to see what an exponential function is. It's a bit different than a linear function, which we've seen before. So first off, we have a table here, and we're going to look at growth and decay. Growth is when we look at our y values, or f of x values, make a note here, f of x, those are getting bigger, okay? So it's increasing by 4, increasing by 12. So this is showing growth because y values are getting bigger. Okay. Here you go, we have another table here. Let's check our y values. That's going down, so minus 20, minus 4, minus 4/5. Okay, so this is what we call decay. Because y values are getting smaller. Okay, so growth means that we're getting bigger, decay means that we're getting smaller, and when we start looking at models of exponentials, it'll make more sense of why we use the words growth and decay. Now we have one more table we're going to look at. This one's a bit odd because it would seem like we are adding 10, we're adding, what is that, 7.5. But this is, we're going to call this one decay. And this is going to make more sense when we look at graphs of exponential functions in a week or so. But we're going to call this decay because the y values are getting closer to 0. Okay, so we're going to let that sit for today, and we'll revisit that when we start looking at graphs of exponential functions. Now, we're going to look at something that we call the differences. Okay, so if we recall differences, we see those in subtraction. And so we're going to do things called first difference and second difference. And so once again, we're going to only mess with our y values. So I'm looking at our y values here. And if I'm looking, take my second number minus the first number. So here I've got plus 4. Here I've got plus 12. Here I've got plus 36. And here I've got plus 108. So that's what we call the first difference. Let's go ahead and do it again. So that is plus 8, plus 24, plus 72. That's the second difference. Okay. Now the reason why we look at first differences and second differences is we want to see if there is an exponential function. Okay. We know there's an exponential function when when the first and second differences have a pattern and aren't constant. Okay? So if I'm looking here, I see this pattern of 2 times 3 is 6, 6 times 3 is 18, 4 times 3 is 12, 12 times 3 is 36, 8 times 3 is 24, 24 times 3 is 72. Okay, so since we don't have a pattern, or don't have a constant, and there's a pattern going on there, we know that we have an exponential function. Okay, let's go ahead and look at another one. Okay, So our difference here, in this case, it's negative. So minus 24, minus 12, minus 6, minus 3. It's our first difference. And then we have minus 12, minus 6, minus 3. Second difference. Okay, notice how we have a pattern here again. We see that pattern repeat itself. Okay, so this is an exponential function. Okay, exponential function. Okay, because we have that same pattern in our first and second differences. Let's take a look at another one. Look at our first differences and second differences. So my first difference, 4 minus 1 gives me 3. 9 minus 4 gives me 5. 16 minus 9 gives me 7. And 25 minus 16 gives me 9. Okay, so there's our first difference. So we might already see a pattern here. Let's go to our next difference. So we have 5 minus 3 gives us 2. 7 minus 5 gives us 2. 9 minus 7 gives us 2. There's our second difference. Now, we notice here that our second difference is constant. And we said that an exponential function is when the first and second difference have a pattern and aren't constant. Okay? So this constant here in the second difference, it tells us that this is not an exponential function. Okay? So we're looking for those first and second differences to determine, is it an exponential function or is it not an exponential function? Now we're coming down to the thing that makes an exponential function an exponential function. And we'll see these listed more in our equations, okay, when we look at those in a bit. But we're going to only look at the patterns here. So the common ratio is the pattern of repeated multiplication or division. Okay, so those are the features that we saw with exponents in their properties this past week. So let's take a look at our table here, and we need to figure out how we're changing. What is our pattern? Okay, so a great way to find our pattern is to take two terms and divide them. So we're going to take 8 divided by 16. If I simplify that, that's going to give me 1/2. Now, it's good to identify that, but let's go ahead and check it somewhere else. Okay, we want to make sure this pattern is consistent. Okay, so I take the second one over the first one. So 2 divided by 4 is the same as 1/2. Okay, so we can go ahead and write down that the common ratio is 1/2. Okay, so that is our pattern. If we multiply by 1/2 each time, we're going to get the next term in the sequence. Okay, or the next term in our exponential table. Let's go ahead and look at another table. Okay, and do the same thing. I'm going to look at, here's a y value. Here's a y value that comes right before it. 9 divided by 3 equals 3. Okay, so let's go ahead and check by checking another y value set. So 243 divided by 81 equals 3. Okay, so now we have a common ratio of times 3. Now let's look at one more table with our common ratio. All right, so we take a y value divided by the y value before it. So we have -1 divided by -3 is 1/3. Okay. Let's go and look at another y value, and then the y value directly before it. -1/9 divided by -1/3. Okay, so we're going to get a bit crazy with our fractions here. fraction divided by a fraction, but this is actually going to give us 1 over 3. So we do have a pattern here. And here's our common ratio, times 1/3. Okay? So that's the pattern that we have going on here. Now we're going to look at one last thing here. We're going to try to find our y-intercept from an exponential table. So sometimes it'll be easy for us. Sometimes it won't be as easy. Let's go ahead and first recall what the y-intercept is. It's when x equals 0. Okay? So our y-intercept here, well, it's already pointed out for us because x is 0. So our y-intercept is 0, 9. So that one's nice and neat for us. Let's take a look at this next table. So I see a problem here because we don't have 0 in our x values. Okay, so that means that we need to do a couple things. We need to figure out what our common ratio is. Okay, so our common ratio, we said 25 over 5 is 5. And then we have 625 over 125 equals 5. So the common ratio of times 5. Now, the tricky part here is that we need to go backwards. We need to figure out what 1 and 0 are. Okay, so I'm going to go ahead and write those in our table. 1, actually, I'll write a new table. 0, 1, 2, 3. We know that 3 is 25. We know that 2 is 5. So if we multiply 5 to go to the right, we have to do the opposite. Okay, so let's go ahead and show that. Divide by 5. Divide by 5. 5 divided by 5 is 1. And then we want to divide by 5 one more time. Okay, and that's going to give us 1 over 5. Okay, so our y-intercept is 0, 1 over 5. We got one last table we're going to look at. Negative 116, 1, 4, 2, 2, and 3, 1. So once again, we don't see 0 in our x values, but I'm just going to be able to kind of stick in our 0 right in the middle here, between negative 1 and 1. Okay, so let's get and figure out what our pattern is. So if I'm going backwards from 1 to 2, I always think about multiplication and division. So I think that's probably times 2 here. Okay, our pattern still is times 2. And then we want to fill in this blank spot right here of times 2. And then 4 times 2, that value is going to give us 8. Okay, so our y-intercept here is 0, 8. With finding y-intercepts, it really comes down to recognizing the pattern and either working backwards or forwards or looking for somewhere in the middle. Okay, so got a few questions to answer on exponential tables.